thank the organizers for inviting me, and it's always a pleasure to come to ITAMP. I'm not sure if this is on. Okay. So today I'm going to tell you about my observation of quantum Hawking radiation and its entanglement in an analog black hole. And this is the world's first observation of Hawking radiation in any system. So this observation builds upon a rich theoretical background, starting with Jacob Bekenstein, who invented the field of black hole thermodynamics. He pointed out that a black hole has both entropy and temperature. And Stephen Hawking then did a calculation showing that the black hole should radiate like a black body at the very temperature predicted by Bekenstein. And in performing this calculation, Hawking combined general relativity with quantum field theory. And so this phenomenon is seen as a first step towards a quantum theory of gravity. The problem is it's very difficult to observe. It seems almost impossible to observe Hawking radiation from a real black hole, because a black hole of a mass of a few solar masses will have a Hawking temperature of less than a microkelvin. So it will be completely overshadowed by the cosmic background radiation. So but the Hawking temperature is higher for a smaller black hole. So if one can find a very small black hole, then perhaps one could observe Hawking radiation. For example, perhaps there are primordial black holes which one can find. Or maybe at the LHC, the black holes might be produced. Then one could observe Hawking radiation. But in 1981, Bill Unruh came up with the idea that one can make an analog black hole in the laboratory where sound plays the role of light, and observe the Hawking radiation in that way. He wrote in his 1981 paper, "Black hole evaporation is one of the most surprising discoveries of the past 10 years." So at the time, Hawking's calculation seemed to be very surprising, and Unruh was looking for a way to check it. So there have been many systems considered since that time that could serve as an analog black hole. One possibility would be Bose-Einstein condensates, or maybe they're superfluid helium-3, an electromagnetic waveguide, ultra-cold fermions, rings of trapped ions. Slow light in an atomic vapor was considered for a while as a possibility. Light in a nonlinear liquid, exciton-polariton condensates. Furthermore, the analog black hole can have more than one horizon. It can have an outer horizon and an inner horizon. This is an analogy with a charged black hole. And in that case, the two horizons can act like a resonator for the Hawking radiation, like a laser resonator. And the Hawking radiation can amplify itself, creating more and more Hawking radiation. And this effect is called black hole lasing. And this was also considered theoretically. And the black hole the black hole laser can be in a ring configuration also. So on the experimental side, my group has been studying this problem, and only this problem, since 2009. And our study has been systematic. We started out by creating sonic black holes, and then we learned how to create and observe small numbers of phonons, since the Hawking radiation consists of phonons. And then we were able to see the naturally occurring naturally occurring phonons, which occur just due to the finite temperature of the condensate. Then we combined our phonon work with the black hole, and we were able to observe the black hole lasing with those two horizons, the self-amplifying Hawking radiation. And now, with improved stability and sensitivity, we can observe the quantum Hawking radiation and its entanglement. So, another system under study experimentally is surface waves in water. This is a classical system where one can create a horizon and shine water waves onto the horizon, project water waves onto the horizon, and see the mode mixing at the horizon. Nonlinear optical fibers is an area where they're looking for Hawking radiation, as well as in exciton-polariton condensates. on the theoretical side, recently, entanglement, the entanglement of the Hawking radiation has been under study. And I proposed last year, I wrote this paper explaining how one can measure the entanglement of the Hawking radiation, and I implemented the technique that I proposed here. So, now this slide just discussed in general the field of analog gravity. How does analog gravity provide input to real gravity? What do we learn about real gravity from analog gravity? Well, here's a list of achievements to date. So far, there's the theoretical result that Hawking radiation is not sensitive to Planck scale physics. In other words, we've learned from analog gravity that by studying Hawking radiation, we don't learn anything about very short ultra short wavelengths like on the Planck scale. Another result is a white hole horizon in water was seen to mix modes. Hawking radiation actually occurs. That was the self-amplifying stimulated Hawking radiation that I saw previously. And the two achievements that I'll be discussing today is verifying the thermal Hawking spectrum and measuring the entanglement between the Hawking and partner particles. Hawking radiation is pairs, which are entangled. Other achievements very recently, seeing a stimulated emission by a white hole horizon. This is also in water waves, as well as observing superradiant scattering from rotating black hole analogs, which is also in water. So some goals are simulating cosmological particle creation and simulating wormholes. So here is the analog black hole that I'll be discussing today. This is a Bose-Einstein condensate, which is long and thin, like in a tube-shaped volume. And it's flowing from left to right. This is just a few thousand atoms, and it's flowing from left to right. In this region, it's flowing subsonically, and in this region, it's flowing supersonically. So if we consider a sound wave, a phonon, here on this side, it can go against the flow because the sound wave travels at the speed of sound relative to the fluid, and the fluid's flowing subsonically. And this phonon has positive energy, like a usual phonon or a usual photon that we're used to. Now, on this side, however, a phonon traveling against this supersonic flow, while it might be moving forward in the co-moving frame, it's falling backward in the laboratory frame. And this is analogous to a photon trying to escape a real black hole. So this is the black hole analog. This is outside the black hole, and this is inside the black hole, and this is the horizon. Now, a phonon, which is inside the black hole and trying to move against the flow but falling back, the frequency is very much Doppler shifted by this fast flow. And it's Doppler shifted so much that the frequency is actually negative. The wave is going the wrong way from what it's trying to do. So the frequency is negative, so the energy of the photon is negative. So one can consider a pair of these photons. One of these negative energy photons, or phonons, in the case of the analog black hole, and photons in the case of a real black hole, it's the same thing. The negative energy phonon inside the black hole and the positive energy phonon outside the black hole. And you could have a pair with zero total energy. So this process can happen spontaneously. You don't need to supply any energy to get the emission of these pairs. So for Hawking radiation, as Hawking envisioned it, it should be stimulated by vacuum fluctuations. So what are vacuum fluctuations in the case of this BEC? So here, this is a BEC with phonons. We've created these phonons. This was in our work leading up to the observation of the Hawking radiation. We learned to create and observe these small numbers of phonons. So this BEC has phonons, and that means it's not vacuum. When we say vacuum in this context, I mean that there are phonons. It's a phonon vacuum. So this is not vacuum. Here is vacuum. There are no phonons in this case, a BEC without phonons. And so one might say, well, this is a BEC with no phonons, so the macroscopic wave function is some smooth function, and so there are no fluctuations. So where are the vacuum fluctuations? Well, if one looks very closely at this BEC, zooms in, you can see that the BEC is actually composed of point-like atoms. And on top of one of the atoms, the density is almost infinite, and between the atoms, the density is essentially zero. And every realization of the experiment, there's a different configuration of these point-like atoms. And these are the vacuum fluctuations. Even with no phonons, the condensate is still made of point-like atoms, and so there are these vacuum density fluctuations. So what Hawking radiation would be, the creation of these pairs of phonons stimulated by the quantum vacuum fluctuations. So how does one observe these pairs? It's very weak. There are very few phonons, and it's a thermal distribution of phonons. It's not like some specific wavelength that's being emitted. So how does one see this? Well, it was proposed in the literature. One computes the correlation function, the density-density correlation function. So one looks at a pair of points, one ideally, most importantly, one outside the black hole and one inside the black hole. And if the pairs are emitted from the horizon here. So if one looks at points which are equal propagation times from the horizon, then one should see correlations. And any pair of points that are equal propagation times, there could be farther from the horizon or closer to the horizon, as long as they're equal propagation times, you should see these correlations. So in here is a correlation function as a function of x and x prime, the position of these 2 points, and there's a line of points. These are the points which are equal propagation times from the horizon. So this is how you see the Hawking radiation, you see these correlations between the partner particles inside and the Hawking particles outside. So what I showed in my paper last year is that one can also measure the entanglement of the Hawking radiation from this very same correlation function. What one does is, basically if the correlations are strong enough, then the state must be non-separable, it must be entangled. So this is a position space observation of the Hawking radiation. So if we merely take the Fourier transform of this feature in the correlation function, then we get sort of a K-space observation of the Hawking radiation, the correlations in K-space. So here's the Fourier transform of this of the correlation function. Okay, actually this is the Fourier transform. One takes the simplest way is just take the profile of the correlation feature like this, and then take the Fourier transform of this. So here's the Fourier transform of the profile, and that gives us these K-space correlations of the Hawking radiation. And then here's a non-separability criterion. If this criterion is negative, then the Hawking radiation is non-separable, it's entangled. So if these correlations are larger than the population, so this is negative, then it's entangled. And this is equivalent to the Paris-Horodecky criterion. So there was an assumption made here in this derivation. What one actually gets by computing that Fourier transform of the correlation function, one actually gets this sum of 4 terms. But we can neglect these 3 terms. And why can we neglect them? Because these are correlations between waves of different frequencies. So here we're looking at the condensate, at the analog black hole. This wave has the same frequency as this wave, because Hawking radiation produces these waves of the same frequency. Or one might be, you can say, is a negative frequency, and one is a positive frequency, but the same absolute value of frequency. However, this wave, going the other way, has a different frequency from this wave because of the Doppler shift. This is a flowing condensate. So this wave does not have the same frequency as this wave, the wave going the wrong way, with the minus. So, for example, this term is 0. This term is correlations between waves of different frequencies. And so it's hard to think of something in this system which would produce correlations between waves of different frequencies. Hawking radiation certainly wouldn't produce such correlations. So it's safe to neglect these terms. So in other words, this method of observing entanglement is valid in an inhomogeneous flowing condensate. This is not a general method for observing entanglement. It's specific to this problem. Now, furthermore, one would like for observing entanglement to measure some non-commuting observables. And in this case, the non-commuting observables are these correlations which do not compute with the populations, so that one can measure this delta criterion. So now the experimental technique. How does one create this analog black hole? Well, so one has, this is a step, okay, the condensate flows over a step. What we found in 2010 was that a great way to accelerate a condensate to supersonic speeds is to let it flow over a step potential, like a waterfall. And after it's flown over, it's going really fast, faster than the speed of sound. And in this case, the step is created by this blue laser beam. So this is a laser beam coming out at us. and it's been cut in half by a knife edge and then imaged onto the condensate with high-resolution optics, Na.5 optics. And then this whole laser beam is caused to move at a constant speed by means of a high-resolution acousto-optic modulator, for those people who work with optics. And so, which allows one to both move the laser beam and maintain this very sharp step. The reason we use a blue laser beam is because it can make a sharper step. And the blue laser beam is a repulsive potential for the atoms because it's blue from the atomic resonance. So it's useful to consider the reference frame where the horizon is not moving. So the blue laser beam is not moving, but the condensate is moving to the right. So in that reference frame, one can say the condensate flows slowly to the right and then pours over the step and gets accelerated to supersonic speeds. And we also have imaging. So imaging, phase contrast imaging at 780 nanometers with high resolution optics. And there's a laser beam, an attractive laser beam because it's red detuned, and it holds the condensate into this tube-like volume. But however, we want very low densities for this experiment. So this trapping laser beam is very weak, and it's not strong enough to hold the atoms against gravity, not nearly strong enough. So we also have a magnetic field gradient, which cancels gravity. So here are some numbers. The speed of sound outside the black hole is 0.57 millimeters per second, whereas the flow velocity to the right is 0.24 millimeters per second. So this is very much subsonic flow. However, inside the black hole, the speed of sound is 0.25 millimeters per second, and the flow velocity is 1.02 millimeters per second, so the flow is very much supersonic on this side. And this is a one-dimensional system, since the trap frequency in the radial direction is 140 hertz, but the maximum interaction energy is only 70 hertz, so the radial degree of freedom is frozen out. Now, also if one zooms in here on this, okay, this is a profile of this image. So this is just the integrated profile. And the blue region here is where we're going to see the Hawking radiation outside the black hole. And the red region is where the partner particles are seen. And if we zoom in on the horizon here, we can see that the horizon is a few healing lengths in width. A healing length is the length scale associated with this interaction energy. And so it's a few healing lengths. That implies that it's hydrodynamic, approximately hydrodynamic, which means it's close to analogous to a real black hole. And furthermore, the step is similar to the green line, which is a gray soliton. If there are any BC people in the room, it was predicted in this theoretical work that this horizon region should be similar to a gray soliton, and it is. So we're going to discuss two types of experiments here. One is the Hawking radiation experiment. That's where we move the step at a constant speed, as indicated by this black line. It's a function of time. The position of the step is a straight line. And we'll also do what's an oscillating horizon experiment, where we're going to generate waves. And the way we're going to generate waves is by causing the horizon to oscillate at some specific frequency. So instead of just moving at a constant speed, it's also going to have a sinusoidal oscillation on top of it. And the oscillation has a 1 micron amplitude, and we can apply various frequencies. And this oscillating horizon experiment will generate waves traveling out of the black hole and into the black hole, so we can see the modes that we expect to see in our Hawking radiation. We learn about the modes of the system. So here, let's start with the oscillating horizon experiment. Here's what the correlation function looks like in that case. This quadrant is correlations between points outside and inside the black hole. And the green rectangle is where we're going to see the Hawking radiation eventually. So you can see this wave type of pattern, because they're both waves outside and inside the black hole. And we can compute the wavelength merely by taking the 2D Fourier transform in the green rectangle, and we get the wavelength in the vertical direction, which is inside the black hole, and the horizontal direction, which is outside the black hole, for the applied frequency that we've caused the horizon to oscillate at. So we could trace out the dispersion relation. So this is the dispersion relation outside the black hole. And here, these filled circles are the dispersion relation inside the black hole. These are the negative energy modes partner particles of the Hawking radiation. So the dispersion relation is not linear. It rolls over here because of the dispersion relation of a BC is not linear for large K. So there's some maximum frequency that we can have for our Hawking radiation. And that maximum frequency corresponds to a maximum K. But we see that the wave packets are sort of wide, and so they actually extend beyond the peak of this K. They have some width in K space, which probably results from the width in frequency space because of the finite duration of the experiment. Anyway, we can see the maximum K that we would expect. Say over there in this corner is the maximum K that we might expect in our Hawking radiation. Another thing we can see from this oscillating horizon experiment is check the rate at which phonons are created as a function of frequency. So here's the rate that the black line is the rate at which phonons are created as a function of frequency. And we can compare it with what we're going to see in the Hawking experiment, because it's the same horizon which is producing the Hawking radiation is producing these waves. So there should be some relationship. So one would expect that this oscillating horizon experiment, this would be the expression for the rate at which the waves are produced, where beta squared is the population of the Hawking radiation in the Hawking radiation experiment. So this is a function of the Hawking temperature. So we plug in the Hawking temperature this is a Planck distribution. We plug in the Hawking temperature into the Planck distribution from the Hawking radiation experiment, and we get the dashed curve, which agrees well with the measured rate within an overall constant. So the horizon is acting the same in these two experiments. So now let's go to the Hawking radiation experiment. We move the horizon now at a constant speed and look for the spontaneous Hawking radiation. And here's what the correlation function looks like in this case. This again is the quadrant with correlations between opposite sides of the horizon. And we see this line that we expected of correlations, this gray region, emanating from 0. So these are the points of equal propagation times from the horizon. And so these are the correlations between the Hawking and partner particles. This is the observation of Hawking radiation. And this correlation function was computed from an ensemble of 4,600 repetitions of the experiment, requiring 6 days of continuous measurement. So we could look at the angle now of this feature. We could just study this feature a little bit. We could look at its angle by integrating along lines at various angles, as shown in this plot. And there's a certain angle here where the minimum is. That's the angle of this feature, and it's indicated by a green line. It's also indicated here, this angle, it is indicated by the dotted line. And these filled circles are the angles that we saw in the preliminary experiment. So we see this good agreement between the angles in the Hawking and the preliminary experiments, and this implies that the phase velocities was the same in the two experiments. The ratio of the phase velocities of the Hawking and partner particles, because that's what gives the angle of this thing. So another thing that we can notice is that the profile of this feature has a finite area. It's not like in the preliminary experiment where you had this sinusoidal pattern where it doesn't have some finite, well-defined area. But here it's a feature this is the profile of this. This is a feature with a well-defined area. So from this expression, this side of the expression is a constant, some finite non-zero value if we plug in k equals 0, so for low k. So this side of the expression is a finite value. This side is something that it's like the population, and this is a property of the condensate, the static structure factor, which goes like omega. So since this side is some non-zero number, we find that beta squared goes like 1 over omega, so this is thermal behavior for very low frequencies, which we just get because the area of this is some non-zero constant, some non-zero number. So we can also compare this with simulation. So one sees a qualitatively similar feature in a simulation of the Gross-Pitaevsky equation. And also the profile looks similar. And in the simulation, you could ignore these fringes. They're an artifact which occurs due to the way that we introduced the fluctuations into the simulation. We repeated the simulation many times, introducing fluctuations each time. And furthermore, we introduced the fluctuations into the simulation at a time well after the creation of the horizon. So that shows that the Hawking radiation is a stationary effect. It occurs with just a approximately stationary flow well after the creation of the horizon. So now we can measure the population of the Hawking particles, the Planck distribution. As a Hawking radiation, if it came from a real black hole, would be like a Planck distribution. And so in this area where we saw the Hawking radiation, we could compute the power spectrum of the fluctuations over the ensemble. This is a technique which we developed for doing thermometry or measuring Hawking radiation when we were working up to observing Hawking radiation. So this is the power spectrum, the static structure factor, and it's proportional to the population plus 1. So we can, by measuring the power spectrum, we can extract the population. So here's the power spectrum, the solid curve. And the first thing that one notices about this power spectrum is that it slopes downward from right to left. And this is a sign that it's dominated by quantum fluctuations, the power. Because a thermal distribution of power spectrum goes up as the energy goes down, like a Planck distribution. So we see this quantum fluctuation. 0 is the pure quantum, is 0 temperature with no thermal fluctuations or no phonons at all. And so the best fit to the data is this 0.36 mc squared or 1.2 nanokelvin. And so by taking the ratio of these two curves, we can see the population. So here's the population as a function of k, and it fits well to the Planck distribution, which is the dashed curve. And the measured Hawking temperature is 1.2 nanokelvin. So now we could go to measuring the entanglement. We have the populations, and we can now get the correlations. And all we need to do is take the Fourier transform squared of the profile of this correlation feature. So, and we get that. So we plug the Fourier transform in here. We get the correlations. We take the magnitude squared, and then we can compute delta. So the magnitude squared of the Fourier transform of this profile looks like this. So there's the magnitude squared of the correlations. And here, the dashed curve is the population that we measured. So we see that the correlations are above the population for a wide range of k. So that's a sign of entanglement by this delta. This term is bigger than this term. So we can subtract these two curves as here. And so this is minus delta. So positive values here correspond to entanglement. So there's a broad k region of entanglement. We also see that these correlations go to 0 at k max, which was the maximum k that we saw in the preliminary experiment. So that makes sense, that we don't see any correlations beyond that k. And here's in the simulation of the Gross-Pitaevsky equation, there was a similar behavior where k max was approximately the maximum k seen. And another curve that we can notice here is as Monica pointed out, there's a Heisenberg limit for the entanglement. The Heisenberg uncertainty principle puts a limit. So this gray curve is the maximum that one can have for these correlations. And we see that the correlations agree well with this maximum gray curve up here at very high k. So here there's approximately maximal entanglement. And this agreement, since this is the Heisenberg limit, is computed from the Planck distribution, this agreement also implies approximately thermal Planckian distribution at these very high k's. However, as k goes down, then the measured correlations are well below this gray curve. So this is less than maximal entanglement, much less than maximal entanglement. So one can ask, how statistically robust is this observation of entanglement? Well, one possibility would be maybe the temperature, the 1.2 nanokelvin temperature measurement the temperature was really much higher, 2.7 nanokelvin. Then this dotted curve is no longer below the solid curve. But if we go back to our power spectrum measurement, then we see that the 2.7 nanokelvin is well ruled out by the measurement. So that's not a possibility, really. Another possibility would be that perhaps this distribution, the correlations were actually a much narrower distribution due to noise. Somehow it looks wide, but it's really very narrow. In other words, maybe this feature, while it looks narrow, is actually very wide. This is the Fourier transform of this feature. So maybe this narrow-looking line there is actually a very wide line. Then there would be no entanglement, because this curve would be over there. But here's the profile of this feature. It would need to be wider by 90% for there to be no entanglement. But its width with these error bars is determined plus or minus 16%. So, so the possibility of no entanglement is ruled out by many standard deviations. So in conclusion, quantum Hawking radiation is observed. The Hawking radiation is observed through the correlations between the Hawking and partner particles. The quantum nature of the Hawking radiation is verified by observing the entanglement. The experiment is well within the quantum regime characterized by spontaneous emission and entanglement, since the 1.2 nanokelvin measured Hawking temperature was much less than 2.7 nanokelvin. A maximum entanglement was seen at high energies and no entanglement at the very lowest energies. And we saw thermal behavior at both very low energies as well as very high energies. And by the oscillating horizon experiment, we verified some aspects of the measurement. We verified the Hawking temperature by the rate at which the phonons were created in the oscillating horizon experiment. We verified the ratio of the Hawking partner phase velocities by the angle of the correlation features. And we verified the width of the Hawking partner correlation feature by that maximum K that we saw in the two experiments was the same. By simulation, we saw that the Hawking radiation occurs on an approximately stationary background. And we also saw that, again, verified the width of the Hawking partner correlation feature by that maximum K. So what did we learn about real gravity from this? What are the implications for real gravity? First of all, black hole thermodynamics is verified experimentally, at least within the analog case. And so we see a black hole does radiate, and Hawking's calculation is confirmed. Furthermore, the Hawking partner pairs are entangled. And this confirms an important element in the discussion of information loss. The information loss is the question, what happens to information which falls into a black hole? One possibility is it's radiated in the form of Hawking radiation. So the Hawking radiation coming out, the entanglement between the various particles coming out, contains the information that fell into the black hole. But we saw that the Hawking radiation coming out is entangled with something inside the black hole. And that, because of monogamy of entanglement, that prevents the entanglement of what's coming out, because it's already entangled with something else, the thing inside. So in a sense, our measurement that we confirmed that the Hawking partner pairs are entangled, that points out that there really is a problem of information loss. So thank you.
Any questions?
So you claim that the pair has zero energy? And
Yes.
one has negative energy, so how is that actually possible?
Okay, because the talk was short, I took out my slides explaining that. So negative energy means that if you add this type of wave to the system, the energy goes down. And that's true in the case of this very Doppler shifted wave. I give you other examples of negative energy. For example, if you picture particles moving at a constant speed and one of them stops, that's an excitation with negative energy.
Usually when I measure entanglement, I need to measure in two bases.
I forgot to say that part. Or I did say it. Okay, yeah?
So I don't understand how it works in your system.
It's very different from a Bell measurement. It's a non-separability criterion. Here, okay, you are measuring non-commuting observables, which is another way of restating what you're saying, I think. For example, like in a Bell measurement, you measure at two different angles which don't commute, and that allows you to measure the entanglement. Here, the two non-commuting things are the correlations and the population don't commute. If that answers your question.
I'm surprised that you can get it. You just take one picture, which is the density correlations, right? You're just doing.
I only measure density, and density commutes. Yes, all my measurements commute. However, I throw away 3 terms because I make an assumption. There's an assumption involved, and the assumption is that waves of different frequencies are not correlated. That lets me measure something which does not commute with something else. So there's my measurement plus an assumption is like non-commuting measurements.
That I can believe.
Okay. Yeah. Yeah.
Other questions? I didn't understand like how the entanglement was varying with K.
Yeah.
So is there like an explanation for that?
Why is it
Yeah.
why is it not maximally entangled? Well, okay. The theoretical prediction is the Hawking radiation should be almost perfectly entangled except at the very lowest Ks where any finite temperature will destroy the entanglement at the lowest Ks. But I saw much worse than that, much less entanglement than that. There are a couple possibilities. One is I think maybe the finite time of the experiment, the entanglement hasn't formed yet in some sense. And there's no theoretical discussion of this anywhere. So another possibility would just be that something is destroying some sort of perturbation is destroying the entanglement. But the simulation, on the other hand, the simulation saw basically the same thing. The correlations look very similar in the simulation. So maybe it's more related to the finite time of the experiment.
So you're saying that the entanglement criterion also comes from Bress-Hardecki?
Yeah, it's equivalent to that, yes.
So Bress-Hardecki is for two spin 1/2 particles, right?
Yes.
And so I guess I'm just sort of confused because if you're looking at correlations between locations in space that might have different numbers of atoms contributing to those points in space, and
Yeah.
you're also talking about variables that have Hilbert space much wider than spin 1/2.
Yeah. It's not such a simple derivation to show that it's equivalent, but it's derived from the Paris-Hordecki criterion brought into this very different type of system. And I could show you a calculation, and it's not so short. And then there's some approximations made about stationarity to get this criteria. There's some very good approximations made to get exactly this criterion. The expression would just be a little longer if it were the full Paris-Hordecki criterion. But it's equivalent in this situation. Anyway, that last part you don't need to remember. I could show you a calculation showing that it's equivalent.
Is there any way to create a three-dimensional black hole?
Well, yeah, there are certainly proposals. I think the original thought was that the black hole could flow down a drain, and then that would be, I guess, 2-dimensional. So, yeah.
So you said that the outgoing photon is entangled with the ingoing photon.
Yeah.
If the ingoing photon is actually reducing the energy of the system that's inside the horizon,
Yeah.
then isn't somehow what's outside still going to be, what's coming out later still going to be entangled with what came out before?
With what came out before. Okay. Just because of the decrease in the energy? Well, it's these pairs with zero energy.
Right. So the
And-
negative one is
Yeah.
decreasing what's inside the horizon.
Yeah.
And then so what comes out later might...
Entangled, but okay, that's sort of a back reaction kind of idea. You're saying the early Hawking radiation changes the black hole, which then affects the later Hawking radiation and causes entanglement at different times. You could write a paper about that. That's a great idea.